Hi there, this is Mikhail. I wanted to share an interesting profiling and optimization exercise that I went through, mostly just for fun, but also to kind of try and see if it's possible to get any useful information out of this Google Profiler service that we recently connected KAS to. So this is how the default page looks. And this is data from production for KAS, and it shows us the CPU profile for all zones and for all versions. Let's pick the last version. And it's just profiles. Most CPU using profiles and fewer. Like all of them are here. We had 17,000 profiles. That's a lot over the last 7 days. So what do we see here? I mean, the width is what's interesting. This is the 100%, the root of it. And then we kind of, it's called a flame graph. You probably all know that. And we can kind of see what takes time, CPU time in this case. We can quickly like filter through this by kind of ignoring that most of this stuff, because it's just very small and insignificant. So I'm looking at optimizing memory consumption, not CPU profiling. So let's switch to allocations. So we want to reduce the number of allocations that we make. And here we see this column, it's part of the flame graph, that it takes half of the screen. So we can drill down so that we don't see any other things. And so it shows us total allocated bytes by a particular stack trace. So we see that these all are almost the same in terms of width, and that means each of them is not allocating much. And then why is it not showing me the self metric? Maybe is it because, oh, okay, now this, okay, you see, this is showing something interesting now. Self, it shows self of 4 kilobytes in this case, and here nothing. Well, this method doesn't allocate anything, it just calls something. And okay, so we see that this one Paul allocates 4 kilobytes. This one allocates. It's more interesting to look at percentage, 26%. So Paul allocates 2%, no, 0.002%, and this fetch refs allocates 26% of this whole thing, which is a lot. And you also see that that the next things that fetch refs calls, they allocate half. So like half is in this method, and the rest is inside. And inside we see that new scanner allocates a lot. Oops, sorry, how do I go back? Okay, not that far. So new scanner allocates half of that, and chomp bytes allocates half of the above. So we have 3 methods that look suspicious. And something here, split n, strings split n, and strings gen split. Okay, so we have, this is a bit interesting. And let's dig in. But also, I found that there is cow mode self. It makes it even easier to spot the suspicious things, and they're here as well. Same stuff. It's just different stack traces where the same method is called by a different chain of calls. In this particular case, it's get configuration, and this here it's something else. Doesn't matter. Okay, let's look at the code. So I've done the work already, so I will just quickly show you what I've done here. Let's check out this commit. So basically we are looking at checkout revision, check out this package, and this is copied from GitLab. This code just parses reference discovery API response, which GitLab streams over gRPC. But it's a standard Git HTTP API, basically. Git replies with all the refs and the commit IDs for each ref and some other meta information about the repository itself. So we are polling this to get, to learn whether a repository has changed or not on a particular branch. So we know that fetch refs calls that parse reference discovery. So the expensive methods are fetch refs itself and parse reference discovery that it calls. And fetch refs lives here, this thing. It makes a call to GitLab, this gRPC method, and then it just consumes the responses, accumulating the data into a byte slice, and then it passes that as a reader to the parse method that parses that. And it's just an automata that parses it line by line. So I wrote a benchmark for this parser. Let's start with the parser. I wrote a benchmark because that's how you test things and measure things in Go. So benchmark is a test that measures allocations and times the code. So here we just create an artificial input, create a reader from it, tell the benchmarking harness that we are interested in allocations, in recording allocations, not only timing the code. Then we reset the timer to ignore this, to not measure the above code. And then this is the standard format where you loop n times over the code you want to measure. We measure this code, we give it the reader, then we reset the reader to the same data. We don't allocate another reader, which I was doing initially. Wait, this should be that. Interesting. Shouldn't be doing that. I forgot to fix that. So, okay, let's run it. So this is the code as it initially was. It allocates, that's how much it allocates for each call, each invocation, and that's how much time it spends for each invocation, and this is how many times it allocates memory for each invocation. It's just standard Go stuff that it allows you to measure. Then if we add this, we tell so IntelliJ Golang in this case builds the binary, and then we pass builds the binary of the benchmark, and we tell it to call this benchmark, and then we pass this parameter to that program that Golang builds with this benchmark. And we tell it to record the memory profile into a file. And then you can see the full thing, what Golang does here. It calls go to with test and compile output, maybe not compile, what is this? Output, so it builds this binary. And then, yeah, it builds this binary. And in this package, I think. And then it calls this binary. Yes, this is the binary name, like this long thing, saying that it should be verbose and some other parameters. So to run this benchmark with this regex, and then this basically excludes all tests, and then that's what we added, profile, and record the profile. Blah, 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 and that's what it prints. So to open the profile, we do this. Yeah, okay, I need to go back. Yeah, this is the thing. So if we do top 5, let's say it will give us the top 5 allocating. Because it's a memory profile, we're analyzing memory here, so not CPU. These are the most allocating methods, and this matches what Google Profiler tells us. Well, of course, this is the only thing that we run. That was silly. So we do this parse to see the annotated code, and here we see this function that reference discovery parse this function basically that we call in the benchmark, and we see where the memory is allocated. And that's a lot because it does a lot of iterations, like how many? 257,000 iterations to properly measure it, exclude anything that's happening on your computer. Yeah, that's a lot in here. Then this allocates, and that allocates, and split n allocates, which we also saw here in profiler. Split n again. This allocates, of course, because it creates new slices, new backing arrays for slices. And this also allocates strings. And again the same thing. And here, that's the same, but the outer scope, and this is the same outer scope. Okay, this is how it is. This is what we start with. So what was the number? Let's put that somewhere. Scratch. What we remember. Okay, now let's see what I've done. The first thing, let's check this out. The first thing was to change all the string operations into byte slice operations. And we don't need to allocate a string here. We just work with the byte slice. And the same here with, yeah, we just change bytes split into string, strings split into bytes split, and everything else stays the same. And okay, let's run this benchmark again. And this is worse. It makes more allocations. Scratch. But it works a little bit faster. It may be not really, but whatever. So it's worse. Okay, why is it worse? Well, probably because we have to cast, change byte slices to strings here, for example, anyway, and here as well. So, okay, let's do the next thing. The next thing is, let's force checkout. And the next thing is, I decided to check because I don't need any of that. I only need references. I don't want to collect all the refs and allocate to that slice. I just iterate over the parsed data and call a callback. So I changed the signature of the function to just the reader and the callback that consumes the data. We no longer collect anything here and no longer collect references or capabilities. We don't need that. GitLab, this is from GitLab, as I said, needs that, but we don't. So I just removed that and simplified the code, and also replaced split n with the cut method. It was added in Go 118, and let's first wait. Let's look at bytes split n. Split n uses gen split. Oh, by the way, gen split, we saw that here, but it was for strings. But with slices, it's the same basically, and they both allocate a slice of byte slices. It's like a two-dimensional array basically. It's an array of arrays, and this is memory that we don't need to allocate if we use the cut, because cut just slices the input slice into two pieces. So it looks for a separator and returns a beginning and like what was before the separator and what is after the separator, and if it was found or not. So you don't need to allocate any memory, just slice it where the separator is. So that removes a single allocation, but it was used in multiple places. So it's a new method in 118, which is quite useful and uses less memory. I also found that moving this into a variable, package level variable, and that doesn't change anything actually. So this allocation is inlined by compiler basically, somehow, I don't know, magic. So it's so we do two things. Again, a callback plus cut instead of split n, and we remove all that stuff that we don't need, that capabilities, collecting references, and I think that's it. Yeah, right, is that right? Yeah, I think so. Yes. Okay, let's run the benchmark again. And yeah, this time I used the reader here correctly. The first time I forgot to change in the first commit. And this is iteration 3. Okay. No, this is iteration 2. This is doing fewer allocations, and it's a little bit faster, but it still allocates a lot of memory in those few allocations. But okay, let's open the the profile, and we see that memory is consumed here, allocated, sorry, here and here. So new scanner and scanner scan allocate memory, and maybe a few other things, but maybe not, but these two things. Okay. The next thing we do is we go to the scanner, and we immediately see that this is an allocation. Oh, sorry. It allocates a 65 kilobyte slice of memory on each time it needs to scan. And then the scanner scan calls this split method, and this thing also allocates memory somewhere here. Okay, I don't know where, but let's first, we can just see that. That's where it allocates memory on this line, and it's here, right? We just change the cast the byte slice into a string, and that's where we waste our memory, spend our budget. Okay, let's check out the next commit. What we've done here is we've stopped wasting memory by pooling the buffers, and that is done like this. Using sync pool, we reuse, it's a memory, it's a free list, basically. It's a list of free buffers. And if the buffer is not available, this function is called, it creates a new one. And we have helpers. We already used that for 32 kilobyte buffers, which we use for all IO. And this we use now for parsing. And then we just use that pool here. And yeah, this is just plumbing to pass the pool instead of this allocation. This is just adjusts the test. Okay, let's run the benchmark. So we still make 6 allocations, but you know, we allocate way less memory, and this function runs 10 times faster now. Not bad. Okay, let's look at the profile again. List parse. Parse doesn't allocate memory. Scanner doesn't allocate memory, but scan still does. How is this thing called? Splitter. Yep, this allocates. Okay. So this string is allocated, the data is copied from the slice, the string is parsed, and then the string is immediately thrown away. Wouldn't it be awesome if there was a method to parse a byte slice into an integer, not a string, right? We would just remove string here and use that, but there is no such method. And if you really care about this, which we probably don't, but just for the sake of exercise, let's say we do. And not reset, check out. So what we've done here is, this is the diff, is a little bit of unsafe magic. So let's look at the code, not at the diff. So a byte slice is actually this thing in memory. It's a pointer to the backing array, length of the slice, and capacity of the slice. So pointer is 8 bytes on a 64-bit machine, and these two are also machine-sized words. So 24 bytes in total, 3 by 8. And we need a string, and string is the same thing, except it does have capacity. It just has length. So pointer and length. So why won't we reinterpret the memory? We can pretend that what's in memory is actually a string and not a slice. In C that would be, and in C++ that would be a reinterpret cast basically. So we can do that in Go by going through the unsafe pointer. So we take the pointer to the slice memory that's pointing to those three words, and via an unsafe pointer cast it to a pointer to the header. So compiler thinks it's a byte slice, a pointer to a byte slice, then compiler thinks that it's a pointer to this struct, which it is. Then we construct a string header, which is what a string is basically, a pointer to the same backing array, and then use length as the length, obviously, and not, we don't need capacity. That's the length of the string. It can't change, it's immutable. So capacity that is not needed. Then this is the string basically, and we now need to turn it into a string so that we can pass it to a method. That we do that by taking a pointer, so pointer to what is a string, to that header. Via unsafe, we can cast it to a pointer to a string, and then we dereference that pointer. So this becomes a string. Then we just parse that string. I have also changed, it was a parse int. Parse int uses parse uint after looking at the sign and doing some overflow and stuff here. We don't need any of that because we already know that it's an unsigned integer. This is 4 hexadecimal characters. So we directly use parse uint. Yeah, this is a little bit of magic, but I think it's worth it, at least as an exercise. And let's see. This is now last iteration. 4. And it's a single allocation, 24 bytes, and it's even faster. Okay, what is those 24 bytes? Top 5. Well, we allocate memory when we put list parse. Nothing here. And that's, can we check this thing again? So, okay, it doesn't have this method because it doesn't allocate any memory. The profile doesn't have this method. How do we know what allocates here then in this method? That probably is the closure. Maybe that's the closure. Yeah, probably that's just this closure. What can we move it out just to better understand what is happening here? Probably it's not the closure, but let's just. No, it's still one allocation. So it may be. Wait, we know, right? We know that it's this thing. It allocates 95 and 98%, and when it puts yeah, when we put a slice of bytes into that thing, in the code, the method will wrap it into an interface here, and that's what allocates, I think. So we can't really do anything about it. Don't think. Anyway, you can see more. If you want to look at the code, there is a merge request for it. Linked in the description. Thank you very much.